Hello, everybody. Welcome to TWSS 21 or 2021, I guess. My name is Colleen Dunn. I am the sales coordinator here at TechX, and I want to thank all of you for coming in and watching us today. We have a very special event, and we have a very special guest speaker today. I want to introduce Maxim Lobok, who's going to be doing our keynote presentation. Hi, Maxim.
Hi, Colleen.
How are you today?
I'm fine, thanks.
So Maxim, I'll give you guys a little background. He graduated from the Faculty of Physics of Moscow State University with a specialty in plasma physics in 2005. He defended his PhD thesis on adaptive grids modeling in the Keldysh Institute of Applied Mathematics of Russian Academy of Sciences. From 2015, he's worked as a research fellow in the Lebedev Physical Institute. In 2020, he won the NG Basov Prize for a series of articles on generation of high charge electron beam in a subcritical density plasma through laser pulse self-trapping. So there you go, Maxim. With that note, I transfer it over to you.
Okay, thank you very much, Colleen. Good morning or evening, everyone. Dear Maxim users, thank you to Higgs for giving me this opportunity to share our results. A few years later, we were searching for new sources of X-ray radiation based on laser-triggered electron, because they got broad potential application, including medical, biological imaging, diagnostics, material science, probing of dense plasma, and even laboratory astrophysics. Sorry. Next slide. Okay, here we go. So it's well known that rarefied gas targets are optimal for electron acceleration to high energy, and they generate high quality electron bunches and through laser wake field excitation. And the excitation of this wake field is the most efficient when a laser pulse length is order of plasma wavelength, and in this case, relativistically intense laser can expel plasma electrons and create a traveling bare iron cavity. Such 3D structure often observed in particle and cell simulations remains stable for laser pulses shorter than plasma wavelength and laser pulse width. So this regime is called bubble, and it base regime for electron acceleration and X-ray radiation sources. It has several problems, I would say, as the electron energy is growing with gas density decreasing, and the total charge of accelerated electrons is decreased as we decrease the ion density. Also, solid foil targets are not so effective in electron acceleration because it all could be spoiled with pre-pulse, which travels before laser pulse, and it significantly lowers the number of accelerated electrons, actually. So it came for us to decision to search for optimal density plasma, which would give us enough electrons, enough hot electrons for real-world applications, and will give us high charge. So we did full 3D particle and cell VSIM simulations. Each was about on 150 cores and lasted for about 5 to 10 days. We changed plasma density from 5% to critical density. Our plasma was from 10 laser wavelength to 601. We used moving grid and high resolution. The box was well, large enough to fill our laser pulse, which we used. And at the end of the plasma, we always used thin metal foil for laser reflection. The pulse was always the same. It was 50 femtoseconds linear polarized with A025, that this is dimensionless amplitude, which is calculated from intensity of the laser. And the diameter of the pulse was 4 microns. Total energy in the pulse was about 4 joules. Okay, here we go. As you can see, as from the left to right, we changed the density. Here we got 75% from critical. Here we got 10% from critical. And at the right one, it's 5% from critical. And they got these results of high energy electron bunches. By high energy, I mean higher than 30 MeV, because 30 MeV would be enough for create X-ray or gamma source of we needed. So we got this optimum in 10% of the critical density. It was about 7 nanocoulombs, which is quite high compared to Wakefield acceleration. And we noticed that our pulse traveled through this plasma for more than 10 Rayleigh length. As we can see it here, at the beginning, the plasma cavity is filled with laser, ion cavity is filled with laser pulse, and it depletes as pulse travels through the target. So, secondly, we're trying to figure out what kind of physics lies behind this. And we tried to get to find out the injection mechanism. So since all particles were tagged in the simulation, we had this H5 file with all electron phase space, and we found the one we needed with 30 with energy higher than 30 MeV, and we tracked them back from where they injected in the plasma, and well, and try to disturb it. We artificially add a small disturbance in momentum, momentum of each electron that was accelerated in this structure, and started the simulation from that point. And so we've got two sets of points that are solid lines. These are original electron tracks, and dotted ones, the disturbed, the tracks that became after our disturbance of them. And so we, out of this, we got the conclusion that it is stochastic injection in this point. Here we got, as we continued our studies, we got in simulations, we got this matching condition for diameter of the laser pulse, which actually depends on the plasma density and intensity of the laser pulse. So when this matching condition is satisfied, we get this soliton-like structure that can travel through plasma for many Rayleigh length, and it doesn't fall apart. Here we got even more elegant for this more elegant way to derive this from this picture. You can see there's a channel of vacuum inside plasma with different angles. So we got actually light naturally diffracts at typical angle of diffraction, and we got definition of the angle of incidence here, and the Snell law that regulates the passage of light from one medium to another. And out of this, and with a condition of full internal reflection, we once again came to same formula that governs our regime of self-trapping. So next thing we wanted to set is to get X-ray emission from Bremsstrahlung converter and from inverse content effect using our self-trapped electrons. So here we got a bit higher intensity, and we wanted not our laser pulse not to fully deplete, but to refract here on the metal foil to create Compton emission. Here we got this bunch of electrons, and once again we took them out of the calculations. Here we got those electron spectra from first case and second one. Here we can see it's plateau-like, or with medium energy in first case is about 100 MeV, and it's a bit higher for high intensity. We took electrons, phase space of electrons out of VSIM and moved it to Jean for simulation in order to get Bremsstrahlung. Here I've got several plots on here. It's Bremsstrahlung from different converters. If you use a smaller converter, you got higher tail in high energy, but lower number of photons in relatively small energies. And here we've got also, here on the left, it's number of photons, and here is full energy of our X-ray or gamma source. So next, we did try to make a radiography with this source, and we put a platinum twisted box inside a big firm sphere, and using transmissive radiography we got these nice results. We can distinguish this object, which is hidden with quite thick piece of steel. And also got next thing we tried, we also covered with 10 centimeters of aluminum around this twisted box, and also we got nice results which can distinguish in it in both cases, in with lower intensity laser and with the second one. So next thing we tried is to calculate Compton effect. Here we got comparison between Bremsstrahlung from these accelerated electrons and from Compton ones. And the same, we get it's got different because of the laser polarization. We got different angular polarization in transverse and in polarization direction. And also we could distinguish small objects. Here we got just 3 millimeter platinum spheres situated in 20 centimeters from our source, and we're looking at them from 10 meters, and each dot is detector, small one. So next thing we wanted to see when we realized that there is a huge amount of electrons inside our cavity, we decided to look how they emit in synchrotronic way. So basically, it's there are two regimes of laser wake field Betatron. Electrons here travel through plasma quality and accelerated by electrostatic, longitudinal electrostatic field, and they emit as they turn. and during their oscillations. Basically, we get X-rays in kilo eV range. Brilliance is limited due to lower total charge from a laser wake field. It's hundreds picocoulombs, but it has very low divergence. That's very good. Another way to produce it is a DLA regime. The radiation is range is much higher. It's MIV range, but in this case, divergence is significantly higher than in case of Betatron. So up in here, we got once again VSIM simulations with the same laser intensity that was the first time, and the one with the high intensity. Both we get long plasma enough to laser pulse to deplete. We did with the same laser, 30 femtoseconds, 4 micrometers in diameter, and we created a self-trapped laser wake, laser field, and well, to get the information about this Betatron source, we also took 3,000 electrons and used this VSIM feature, which can trace each particle on each step. And well, we dumped it and calculated out of this spectras and other stuff. So here we got projection of trajectories of this. Here we got its slightly beige part where cavity is still filled with laser pulse. And in this case, we don't have higher energy. This color shows energy. And as laser pulse propagates through target, it depletes. And here after we got higher energies. In the polarization, in the plane of laser pulse polarization, we got higher oscillations than in transverse one. And here we got average energy of our accelerated electrons, and it's about 100 and something MIV. So we calculated angular distribution of Betatron. Here we got it for A24 and for A72. It's quite low. Well, it's about 20 mRad and a bit higher for a high intensity laser. But the main feature we got here is the photon energy. Even for this relatively low intensity laser pulse, well, we got hundreds of keV in photon spectra, and for the powerful one, we got MIV here, critical energy, and so this is evolution of electron energy and instantaneous emission power. And here we can see that it starts emitting actively after the laser pulse starts deplete. And at this moment, electrons emit more and more for about 25 microns, and here it's 50, I guess, microns. And it turns out that our Betatron radiation source is very bright compared to other sources of radiation. It's much higher than Bremsstrahlung, and it's higher than Compton, and its energy is also very high. Here we got angular integrated photon spectra and the same plot for energy spectra of electrons in two cases. Once again, we see this Plato-like spectrum, which is typical for our regime of electron acceleration. We did some test particle simulations also to clarify how this works. So at the beginning, we got longitudinal electrostatic plasma field and laser pulse field. Then it depletes, and at the end we got electrostatic, just one. And here we got the evolution of electron energy in two cases, with plasma, without plasma, and we can see it's doesn't play a big role here, and it doesn't really affect electrons. So basically, laser pulse, high energy laser pulse creates this ion cavity, which is quite small. So, and the radius of this cavity goes to critical energy formula, which describes the spectra of emission. Here we've been testing it with without laser pulse, with laser pulse, and the way it depletes, and it's matches well with simulation we did in VSIM, was full particle. Right. So once again, to conclusion, this laser pulse plays a great role in ejecting electrons in our cavity, and it's forming a cavity in very dense plasma, and also it leads to high charge. We could feel it in this cavity. It also polarizes our X-rays, and well, it's a bit increase, gives a bit increase in divergence. Well, and here we got brightness of our source, and it's very bright. turns out I've been a bit quicker than I thought. Well, thank you very much. Any questions?
So there is a Q&A box on the bottom, and if you have questions, you can type them in, and we will be able to ask Maxim and get you an answer. So I do have, Maxim, two questions. So the first question is about the Betatron generation regime. So how stable is your Betatron generation regime?
Well, it's indeed very stable, because in the beginning I was telling that even our self-trapping regime is quite stable with density. We still got, if at the experiment you will have density which higher or lower, we'll still have a high charge, and we still have high energy of electrons. So it should, and it will be stable with this.
Cool. Another question, is there the self-trapping regime in case of non-homogeneous plasma?
Yes, thank you very much for asking this. Actually, we tried, our simulations were with homogeneous plasma. And we did back research to try to start this self-trapping regime in non-homogeneous, in real-world plasma, where we got pre-plasma before ramp or ramp. And I would say if we find we can use this matching condition once again, and to focus using this matching condition on the ramp. And in some cases, you can get even more electrons, or even more energetic electrons in this case. So it could be even better in non-homogeneous plasma.
If anyone else, those were both great questions. If anyone else has others, you can just click on that Q&A box and type them in. We've got Maxim for a little bit longer. And thank you, Maxim, just to say it now, for speaking to us. I know it's dinner time for you, and I know we have attendees that are on from all over the world right now. It looks like some people it's midnight. I've got a couple of people. Wow, we've got quite the audience here. So does anyone else have any additional questions before we let Maxim go? And what? Well, you must have done a very thorough job, Maxim.
Okay, thank you.
Okay, well, on that note, I will let Maxim go unless anyone has anything else. Our next talk will be coming up in an hour at 10 a.m. Mountain Time. And I just want to let everybody know that, Maxim has worked with our software with VSIM. He has, and if this is something that you are interested, if you do not have a license currently, we can certainly get you one. We do offer free 30-day trial licenses. Please go to our TechX website at txcorp.com, txcorp.com, and you can request a free 30-day evaluation of the software that Maxim has been using, VSIM. So thanks again, Maxim, very much for taking your time and sharing this with us. And I will see all of everyone else in attendance. I will see you at 10 a.m. Mountain Time. Thanks so much.
Thank you very much.